For most of human history, space and time were treated as separate things. Space was where events happened. Time was what moved them forward. They felt independent, simple, predictable. Then Albert Einstein changed everything. Not by adding complexity, but by removing assumptions. Einstein realized something unsettling. Space does not exist on its own. Time does not exist on its own. They are not separate stages. They are woven together into a single structure, space-time. This idea sounds abstract, but it explains something very real: gravity. Before Einstein, gravity was treated like a force, a pull between objects. Invisible but simple. Einstein saw it differently. He proposed that mass does not pull. It bends. Imagine space-time not as emptiness, but as a flexible fabric. When something massive exists, it presses into that fabric. The fabric curves, and objects move along those curves. This means planets are not being pulled. They are following the natural shape of space-time. Gravity is not a force acting at a distance. It is geometry. This idea was shocking, because it meant space and time are not fixed. They respond to mass. They respond to energy. They change. Time itself is affected. Einstein showed that time does not pass at the same rate everywhere. Near massive objects, time slows down. At high speeds, time slows down. This is not philosophy. It is measurable. Clocks on satellites tick differently than clocks on Earth. GPS systems must correct for this every single day. Without Einstein's space-time, modern navigation would fail. Yet despite this, space-time still feels impossible to picture, because our intuition evolved for slow speeds and weak gravity. We move through space-time constantly, but we only feel space. We rarely feel time bending. Standing on Earth feels stable, but Earth is moving, orbiting the sun orbiting the galaxy moving through cosmic structures, all of it traced through space-time. You are not standing still. You are following a path through a curved universe. Einstein's equations describe this curvature. They are precise. They are tested. They work. And yet, even with all this success, we still don't fully understand space-time. At the smallest scales, Einstein's theory breaks down. At the center of black holes, the math stops making sense. At the beginning of the universe, space-time becomes extreme. Is space-time smooth? Or is it made of something smaller? Is it continuous? Or made of discrete pieces? We don't know. Modern physics still struggles to unite space-time with quantum mechanics, two correct theories that refuse to fully agree. This is why space-time remains mysterious. Not because it is vague, but because it is deep. Einstein gave us the framework, but the full picture is still unfinished. Space-time is not just where reality happens. It shapes how reality happens. Every movement, every orbit, every signal traveling through the universe. All of it follows the curves Einstein described. We live inside space-time. We move through it. We age within it. And yet, we still struggle to truly understand what it is. More than a century later, Einstein's idea still challenges how we think about reality. Not because it is outdated, but because it was ahead of us. To understand why space-time is still so difficult to grasp, we need to slow down even further. Because space-time does not behave the way everyday objects do. On Earth, distance feels fixed. Time feels steady. A second feels like a second. A meter feels like a meter. But space-time does not agree with this intuition. Einstein showed that space and time adjust themselves depending on motion and mass. There is no universal clock ticking the same way everywhere. There is no universal grid holding space rigid. Instead, space-time is relational. It responds. When something massive exists, it reshapes the geometry around it. Not by pulling on objects, but by changing the paths available to them. This is why light bends near massive objects, not because light has weight, but because space-time itself is curved. Light simply follows the geometry it is given. This idea was confirmed during a solar eclipse in 1919. Starlight passing near the sun was observed to bend exactly as Einstein predicted. From that moment, space-time stopped being theoretical. It became physical. But this physicality creates problems. Because if space-time can bend, stretch, and slow time, then what happens when those effects become extreme? Black holes provide the answer. Or rather, they expose the limits of our understanding. Near a black hole, space-time curves so strongly that paths begin to close in on themselves. Time slows dramatically. To an outside observer, nothing ever truly crosses the horizon. At the center, Einstein's equations predict a singularity, a point where density becomes infinite and space-time breaks. But infinities are warning signs. They usually mean a theory is being pushed beyond its limits. This suggests that space-time, as Einstein described it, may not be the final story. At very small scales, quantum mechanics dominates. Particles behave probabilistically. Energy comes in discrete packets. But space-time, in Einstein's theory, is smooth and continuous. These two descriptions clash. They both work perfectly in their own domains, but refuse to merge. This is why modern physics still searches for a deeper theory, one that explains what space-time is made of. Is space-time fundamental? Or is it emergent? Some theories suggest space-time is not basic at all, that it emerges from more fundamental relationships. In these ideas, space and time are not ingredients. They are consequences. Just as temperature emerges from the motion of atoms, space-time might emerge from deeper informational structures. This would explain why space-time behaves smoothly at large scales, but becomes strange and unstable at small ones. It would also explain why gravity is so different from other forces. Einstein's gravity resists quantization. It does not behave like a force, because it is not one, it is geometry. Another clue comes from the universe itself. Space-time is expanding. Every distant galaxy is moving away from us. Not through space, but with space. This expansion means new space-time is being created. But created from what? Einstein's equations allow expansion. But they do not explain why space-time exists in the first place. The beginning of the universe raises even deeper questions. At the earliest moments, the universe was extremely hot and dense. Space-time itself was compressed. Time, as we understand it, may not have existed in a meaningful way. Before the Big Bang, the question what happened before may not even apply, because time itself may have begun there. This makes space-time unique. It is not just part of the universe. It defines what before and after mean. Einstein gave us the structure, but the origin remains unknown. Even today, we rely on space-time constantly without noticing it. Every satellite orbit is calculated using curved space-time. Every precise clock must account for time dilation. Your phone's GPS works only because Einstein was right. Yet despite this practical success, space-time remains deeply unintuitive. We can calculate it. We can measure it. But visualizing it pushes the limits of human imagination. This is why space-time documentaries often feel calm. They slow things down, because rushing makes understanding impossible. Space-time does not reveal itself through speed. It reveals itself through patience. Einstein once said that imagination is more important than knowledge. Space-time proves this. It forces us to imagine a universe that does not match our instincts. A universe where time stretches, where space bends, where motion changes reality itself. We are not observers standing outside space-time. We are embedded within it. Every thought you have, every memory, every movement is traced along a path through space-time. You are not simply alive in time. You are moving through it. And this may be the deepest lesson Einstein left us. Space-time is not a backdrop. It is a participant. It shapes the universe while being shaped by it. More than a century later, we still do not fully understand what space-time truly is. But that is not a failure. It is an invitation. An invitation to keep questioning the structure of reality itself. Because space-time is not just an idea we struggle to picture. It is the reason the universe looks the way it does. And until we understand it completely, there will always be something left to explore.